Okay, so welcome to this second session about air treatment and purification. It's my pleasure to introduce our first speaker, Ehsan Mousavi from Clemson University. He will give us a talk about entitled A Systematic Review of Evidence on Air Filtration and Recirculation. Ehsan, the floor is yours.
Thank you so much, Marie-Celine. Good day, everyone. Good afternoon if you're in Europe or elsewhere. I'm actually in America, so it's still morning here. And I want to welcome you to this excellent event as well. Very timely and important topic. So let me go ahead and share my screen so so we can start the presentation. As indicated, my name is Ehsan Mousavi, an assistant professor at Clemson University in the United States of America. I'm going to talk about air filtration and recirculation in healthcare facilities. A very timely topic. What I have in mind is to lay out the problem from my, I guess, specific perspective. And I'll call that the introduction. And then I'm just going to go ahead and talk about some of the literature, what has been done, and then also begin talking about a little bit of theory of, to our best of knowledge, what kind of theories are out there for filtration, air recirculation, and then show you some case studies and examples, and then open up for Q&A. I'm sure you'll have a lot of questions. Quite frankly, when I was thinking about this topic and as it relates to the overall theme of this event, I think the most important question that came to my mind was really what percentage, what's the role of the built environment overall, right? Because this problem is going to have a lot of layers and facets to it. So there's say for instance, there's a COVID-19 problem. There is like any contamination in healthcare facilities. What characteristics that the contamination is going to assume? Is it going to be airborne? Is it going to be droplets? So these are great questions. And honestly, I know that these are also super, super hard questions as well. So these are the types of questions that are not easy to find answers for. And then the second one, which is kind of the prelude of what I'm going to present today, is what does the role, the built environment, what kind of role does that play in this whole realm? I mean, as you guys can see, for instance, if you have two rooms in a hospital, and they're somewhat connected with the HVAC system, there's a possibility for contamination spread that goes from one room to another. There has been things of that nature. When we look at the COVID-19 literature, which is still evolving, we'll see that the virus has been detected in some of the reports on the HVAC system itself, meaning that the virus was able to travel in through the ductwork and essentially deposit on some filter here. And the virus was also observed, relatively speaking, 25 feet away from the source. So these are some indications that this specific virus can actually travel far and can assume an airborne transmission route. So with that in mind, let's actually take a look at the literature. Essentially, there was a project, I was involved in it as the principal investigator, and ASHRAE, the American Society of Heating and Ventilation, they essentially gave us some support to go ahead and review the role of building mechanical systems in healthcare facilities. So we reviewed about 1,000 different papers, and I'm just going to give you a nutshell of what we found from that literature review. The first item really that I want to talk about is that the ventilation design parameters, and by that I mean airflow, the rate of air that's coming into, say, a patient room or an operating room or things of the like, and the filtration and the circulation and distribution of air, these are highly interrelated items. So it's hard to study one in silo. They're very connected to each other. And that's really important for us to recognize. The second one is that if we aim for a mere change in only one of those parameters, it can easily result in undesired consequences in other aspects of things. So that's also very, very important. The other one that I have found, and this is to me an interesting outcome of that research, is that conducting what we call randomized research, right, is closely, I mean, it's close to impractical. It's very hard to do something of that nature in a healthcare facility system due to patient safety issues, approvals, and so forth. So that's also another, hurdle towards, what we can potentially achieve. And then one more thing that was really interesting to me was observational studies. Most of them are before-after studies. What do I mean by that? Essentially, a group of researchers took a hospital, they made measurements before a set of renovations, and then they also measurement after. So when something like that happens in the after renovation section, you have all sorts of additions. You have hand sanitizers, you have improved movement, you have air changes that change. So it's there's a lot of confounding variables is what I'm trying to say. And it's not always easy to attribute the findings to filtration or air circulation or things like that. So that's also important to know. And then that's my last point that will actually lead me to my next slide. And that's theoretically, filtration is important. Filter efficiency plays a big role. And I'm going to actually show you what I mean by that in the next slide. So, but the point before I do that, the point is it's hard to take that theoretical perspective and then generalize it to practice. So I just want to lay that out because that's a very important point. Now, some of you might have heard of that term before, well-mixed room. What do I mean by that? So that's a very simplifying assumption. It essentially says if you have a patient room, you're assuming that the contamination spread is uniform in every point of that room. Obviously, it's not going to be the best assumption in the world, but it's one that's going to help us at least shed some light theoretically to the problem. So I kind of take the liberty and did that, right? So I did assume a well-mixed condition just to kind of show you a finding, and then you'll actually get a differential equation that shows the decay of contaminants indoors. The reason I'm showing you this is that a lot of times, and I saw that as a question also from the panel, a lot of times when you have a fixed fan in your HVAC system and you change the efficiency of that filter in front of it, it will create, and if you improve that efficiency, it'll create more resistance, which means that the rate of air that's going through the filter can go down, right? Now, these are coupled problems. So you increase one, but the other one will be affected by that decision. So what I did, I made that assumption, and then I created this graph that essentially the green line shows where the problems are coupled, meaning that improving the efficiency of the filter would reduce the amount of fresh air that's coming into the room. And look at what happens to this time index. This is essentially the time that takes for the room to decay the contaminants to 0.001% of its initial value. And it takes almost twice the time when you include some practical aspects of that problem. Let's look at the recirculation too. So, well, again, that differential equation, I don't mean to go through the math like at all, but essentially it leads to some decay. And we did some measurements and it kind of looks like this. It essentially shows us that particles will decay like exponentially with time within a space. And when we look at it, this gamma, this decay rate, is a linear function, theoretically, of the amount of air that's brought to the space. we call that ACH. Some of you might be familiar with that term, air changes per hour. That's the amount of air that's coming into the space. So we did a number of experiments, and it turns out that yes, that linear performance between air change rate and decay rate is there. You guys can see on the y-axis I have gamma, on the x-axis I have ACH. It's beautiful, right? Then what we did was that we solely looked at this parameter here. So we solely looked at this section, and just so you know, alpha is a percentage of outside air. In other words, if you have 100% air coming from outside, meaning no recirculation, then that term that you see, this term, is going to go to zero, right? Which is good. Theoretically, it's excellent. On the other hand, if filter efficiency approaches 100%, you also, again, this is the filter efficiency. You also can see that term can go to zero, which is, again, really good. But there's an interrelation there that's very interesting and very important. And I was going to talk about it. Our case was right about here, where I had about 25% of outside air in this cases that I'm showing you, and about a MERV 8, which is like 65–70% efficiency. So the reason I tell you this is that the amount of air that's being recirculated is a function of efficiency of the filter. It's important for us to also recognize that aspect. So with that said, let me also show a couple of case studies. This is an experiment we did in a hospital system. And as you can see, we created a plastic barrier shown in this image, and we placed it right here to kind of isolate a patient with a known viral problem or diagnosis. And then we also placed a couple of filters, one inside the isolated space, and the other one we placed it in a space we call anteroom, where the medical staff will don and doff and so forth. And then we tested them. So we turned both of them on. We turned only the isolation room HEPA filter 1 on, and you guys can see the different variations that we tested. The interesting result is that it matters. Actually, it matters very significantly which HEPA filter you turn on and what that system looks like. If you look at this, when both of the systems are off, I have a trend in particles, and this is right at the door, outside of the room. I have a trend of particles that are going up, they're accumulating. Now, if I turn off the HEPA filter inside the isolation space, this one, I get a very similar result. So kind of the outcome of that for me was that if you have only one HEPA filter, put it next to your patient. Put it next to the source, and don't actually put it closer to the door. So that's one outcome that I found. And we also tested, you might have seen this, especially post-COVID, a lot of aerosol boxes. So we tested one of those as well. And that's the structure of that aerosol box. We called it the cover system. And as you might see, there are filters on either side of this cover. And we changed the filter, we changed the fan, and we created a couple of different scenarios. This line, this kind of flat line here, shows when there is no cover. So what happens? How much distribution of contamination do I get in my room? And there's flat and it's high up there, right? But the moment I install my cover, it actually kind of goes down magnificently. But the thing I was going to also, a practical aspect of this that I was going to emphasize is that, well, look at this case. We tested a kitchen fan, a fan that's not like the best fan in the world. It's leaky, but it's practical. You can actually essentially go to Walmart and buy one of them. I mean, it's accessible. Right? We put that, and it turns out that that's not the best idea in the world. To look at the outcome of test 5, it essentially rockets up like that. So it shows that the leakage is an important matter. If you use a cover system like this, make sure that you seal it, make sure the connections to the pump is greatly sealed. If you can actually discharge that air somewhat, like for instance through this window that we had towards outside, do that, because discharging it near the place is not kind of the best thing that we can do. And I think I'm right about time. So with that, I am going to thank you and look forward to having more discussions with you at the end of this session.
Thank you very much for this excellent presentation. I think we'll let the question to the end, and we will move forward with the second presentation, which will be from Emmanuel Vanoli from Dassault Systems, entitled Modeling of Aerosol Transmission of Airborne Pathogens in Hospitals, Impact on Air Treatment, Design and Use.
Thank you. Hello, everyone. I'm Emmanuel Vanoli from Dassault Systems, and I am responsible of all the activities related to airflow and particle simulations. And I will present you today a work we did with the Hospital Bichat in Paris related to 3D simulation of aerosols emitted by a patient in an intensive care unit, and how to mitigate the transmission risk thanks to a different modification of the layout of the room. But first of all, let's have a first introduction about the aerosol issues. We used a 3D simulation technology to predict and assess what could be the risk of aerosol transmission. And this technology is what we can call high fidelity technology coming from the aerospace industry. And we just, try to adapt both know-how and software to the challenge related to internal airflow propagation and particle propagation. And what is difficult with aerosol transmission, let's say, assessments is the fact that, first of all, it's very complicated to perform physical tests inside an hospital, especially in the pandemic context. And if you want to go and use a laboratory, then you will probably miss some important, let's say, factors like ventilation system of the room of an hospital, the layout of the hospital, and probably other parameters that you cannot reproduce inside a laboratory. So we did a very interesting study with the Hospital Bichat at the beginning of the pandemic during the first wave in France. And we were contacted by the head of the ICU department of Bichat. And the professor Tim Seat wanted to have a way to, let's say, understand what could be the air emitted by someone in a negative pressure chamber, and how the aerosol emitted by a patient can propagate inside his room. And what we did is, first of all, to we validated our numerical human model, which is on the right of the animation, with a real physical test done in laboratory at the École Polytechnique. So the idea was to simulate a cough, a sneeze, and so on, with a 3D digital twin of a human model, including a lot of details like the throat, the teeth, and the mouth, and so on, and compare the airflow results with tests done in laboratory. Because if we cannot validate directly the emission of the air, we can be sure that the aerosol transmission will be wrong too. So as I said, we designed a very detailed digital twin of a human body, starting from the throat, and we based our, let's say, boundary condition of airflow emission from some studies done by the MIT. So in this case, I'm showing you a double time cough, like you have the airflow emitted by someone in the animation right here, and the particle distribution that we used. We tried several setups. In the presentation, I will show you 3 micrometers center distribution of particles, but we also tested 0.3 micrometers and 30 micrometers. And if we are comparing the results from the tests and the simulation, we have very interesting conclusion already. Here in this slide, you have on the right the simulation, and what you can see is what we can call a Schlieren visualization, which is basically a way to see the gradients of air density. And on the left, you have the test done in laboratory. So it's a bit hard to see, but you have the nose of the students, the mouth, ear. And we basically compare milliseconds per milliseconds, how the air was emitting, how this density was variating. And we discovered that the simulation was able to reproduce the angle of the jet emitted by the student coughing, but also the velocity of the air, so how far it can travel in time, and some big structures that was always, remaining in different tests done by the students, as you can see in this animation. So it was for us a good way to see that simulation will be able to reproduce already the emission of air by patients. And now, as soon as we can do that, we can put this digital twin inside a negative pressure room situation. So we used to work with the Bichat Hospital staff to create a kind of digital twin of the room, the negative pressure room. So we introduced a lot of details for the ventilation system. Here you have the air injection system. And in this corner right here, you have the extraction of the room. And since it is a negative pressure situation, we also take in account in the simulation the corridor and the gap under the door. It was about 8 millimeters, because of course, then you need to bring the air from the corridor to have an equilibrium inside the room. And we did the first simulation only about the airflow. So the idea was to understand basically what was the propagation of the air inside the room before generating the emission of aerosols. And in this animation, you have the air velocity evolution in time. So the more red you are, the more velocity you have in the room. And we can already see very interesting conclusion. The first one was the fact that because of the inlet vents of the HVAC system, we have a kind of 360-degree propagation of fresh air inside this room, which is pretty good if you want to refresh every corner of the room, but it will have a cost in terms of aerosol propagation. We'll see that a bit later. Then the negative pressure situation is involving a high velocity jet of air coming under the door. And it's creating, as you can see, a lot of fluctuations inside the room, a lot of turbulences, which results around the patients of a very complex airflow situation. But what we can already see is the fact that the combination of this airflow and the heat rejected by the body of the patients is making the air going up straight to the HVAC system. So when we are simulating a cough from a patient, so here in the green bubble is some aerosols that we can reproduce in the simulation, we can see very interesting things too. The first thing is that as soon as the patient will cough, in a very short time, you have the aerosol that will follow basically the initial jet. But very, very quickly, the aerosol will follow the air movement inside the room, will go up to the ceiling, and then it will be propagating in every direction, following, the air injection in the room. And as a result, if you look at the extraction, which is on the top right corner of the room right here, it has an impact, of course. It's, let's say, extracting a lot of particles, but it seems that the influence of this extraction is quite limited in space. And as soon as the aerosols are exiting a kind of influence sphere of this extraction system, the aerosol will then follow the air again, and you will have to wait a lot of time before the aerosol will go again close to the extraction system. And as a result, what do we have in this situation? We can see that after 1 minute of simulation, 50% of all the aerosols emitted by the patient are extracting by this HVAC system. We have a deposition on surfaces around 20%. So you have in the blue some heat points of aerosols at different locations of the room, which leads at the end of remaining particle in suspension of a bit less than 30%, which is already quite good. But then the idea was to try to improve a bit this situation. And the idea we had with the Professor Tim Seat was simply, to change the orientation of the bed. Because since this HVAC inlet was propagating in every direction, we wanted to try to contain as much as possible the particles close to the extraction system. And to do that, we had the idea to align both patient mouth, HVAC system, and extraction. And by doing this simple modification, you can see that we can extract a bit less than 70% of the particles emitted in 1 minute. So it's a lot of improvements with this simple modification. We are increasing a bit the deposition rate, but at the end, we have only 8% of the total particles emitted that are remaining in suspension. So then the Hospital Bichat wanted to know if it was possible to, let's say, assess if it was a benefit or not to add an additional air treatment unit. So in this case, it was a plasma unit. And what we wanted to tackle with the hospital staff was, is it efficient or not? And what could be the best location in the room to put this device? So as you can see, for this particular air treatment unit, you are sucking air from the bottom face and injecting fresh air and clean air from the top face. And the first position or location we wanted to investigate was to put this treatment unit just under the extraction system. And as you will see in this animation, it is a very bad idea. Why? For two reasons. The first one is the fact that we are basically propagating clean air straight to the extraction system. But on top of that, we are creating with this treatment unit an additional ventilation in the room. And this ventilation is pushing all the particles on, let's say, the opposite corner of the room, if you look at the extraction system, which at the end leads at a very, let's say, bad situation in terms of aerosols in suspension, because after 1 minute, now we are only at 18% of the total aerosols extracted by the system or treated by this treatment unit. And we have 60% of the whole aerosol emitted still in suspension. So a very bad location for this treatment unit. But on the contrary, if you still use this treatment unit as an additional ventilation system, so if you put it at the opposite side of the room, so you align the treatment unit, the patient mouth, the HVAC system, and the extraction, then you are able to push and contain much more the aerosol close to the extraction. And at the end, you have 73% of the whole aerosols that are extracting by the HVAC system. And we reduced also the deposition on the surfaces, and we have a bit more than 10% of the whole aerosols emitted still in suspension after 1 minute. And just to conclude my presentation, we are working on many more situations. One with the Hospital La Pitié-Salpêtrière was about, let's say, aerosol transmission in the post-surgery room, so between different patients. And another one, which is published in the American Journal of Respiratory and Critical Care Medicine with the Hospital Avicenne, is about the prediction of deposition of aerosols on surfaces. Thank you.
Thank you for these two excellent presentations. These are brilliant talks. Thank you very much for this.
You're welcome.
We will now have time for a few questions. First, I would like to read a comment from Eladio Gomez. Maybe one of you will have the will to comment about this. So, to be able to detect SARS-CoV-2 RNA in the environment doesn't mean it's still infective. To be able to detect even viable SARS-CoV-2 at long distances doesn't mean that an infective dose can be easily achieved. We must bear in mind that dilution of an eventual aerosolized pathogen doesn't decrease linearly with distance, but to the third power. So this issue is critical in an enclosed area, but the effect of dilution into a healthcare facility is huge. Do any one of you want to comment on this? I think it's an important comment.
I can give it a shot, Emmanuel. Do you mind?
Please go on.
I read that comment. Fascinating comment. Honestly, the first thing came to my mind is that, you know what? That's our best bet. Yes, I know that we're far from perfect in this situation. You're absolutely correct. There's a lot of things related to whether a virus that's detected somewhere in the environment, in the built environment, is infective or not. Is it dead? Is it alive? fantastic things. Honestly, part of it is, as an engineer, is above my pay grade. But I've come to realize that still doing things the way that Emmanuel presented on the computational modeling and experimenting with surrogate particles is our best bet. I mean, I wish we could conduct a series of holistic experiments where there is a real patient, there's a real hospital, everything can be monitored. I find it very, very unlikely to come up with a methodology of that nature. That's why we're trying to, this is a huge elephant. We're trying to break it into pieces, and then one bite at a time, we're eating that elephant. And that's why a lot of interconnections like that are super important. They happen. But that's our, I mean, that's at this point in time, we're doing our best to provide some response to the problem. Is that the best ever response? No, I'm with the commenter there. There's a lot of other items, especially on the biological end of things, that needs to be included. But we're rather, that's a limitation that I have come to accept.
So thank you. So I have also a question from the chat. So what is the practical difference between different types of filters, HEPA 13 and HEPA 14? What is the minimum needed?
Well, that question again, Emmanuel, I don't mean to be talkative.
Go on. No problem. No problem.
Sorry. So that question is partly a code question, right? Especially as an engineer, you have a code that you follow. In the United States, we follow like the FGI, the Facilities Guideline Institute, or ASHRAE codes. They recommend HEPA, like 15. HEPA filter means that MERV rating of 15 and above, right? So they recommend HEPA filters. The difference between them is essentially at the rate by which contamination will be removed. So for instance, if you look at a HEPA 14, you're looking at the lowest possible efficiency. You're looking at about 90 to 95% removal, right? Now you make it better. The real HEPA filters, they go to 99.9% removal, right? So that's the difference. Which one is more efficient? We have to do a lot more to provide a precise answer to that. Right now, codes require, for instance, CDC required hospitals to change what they had to a HEPA filter with a 99.9% removal. How efficient that decision was, we haven't yet evaluated it, at least to my knowledge. That's definitely something up for grab, and we need to talk a bit more about that. But one more thing, and I'll let you go to the next question. Let's bear in mind that these filter media are designed to capture nuclei, like solid particles. So in a future event, if we have contamination that's gaseous, these filters don't work the same way on those types of contaminations. I just wanted to say that.
Thank you for your answer. The next question was, would using a lower grade of HEPA filter mean that the fan speeds could be lower and there would therefore be less energy consumption and noise?
I kind of feel bad. I go for it.
Go on, no problem.
We will have questions for you, Emmanuel.
Yeah, well, let's put it this way. You usually have a fan that's not changing, right? So the power of the fan, especially if you have already a hospital up and running, right? And there are fans in the hospital system. Those fans, they're usually providing the same power, same RPM, and so forth. Now, the matter happens on the other end of things, where when you change the filter media, you create more resistance. The fan is held constant. There's more resistance along the way of air, so the amount of air supplied will go down. So that's that's what happens for the most part. And I have observed that in some of the hospitals around me, and when they wanted to respond to the COVID-19 problem, they just increased the filter from some like MERV 10 to a HEPA filter. That's a lot of pressure drop. So that essentially means that now the amount of air that's supplied to this space is going down. So in a sense, the point you made, the point was made, is correct. But a lot of times in practice, it's the other way around. So the fan doesn't get more energy efficient or less energy efficient. The fan stays constant. The amount of air you get goes up or down.
Thank you.
Yep.
So I will try to read another question, maybe for you, Emmanuel. So where should mobile air filtration system be placed in a multiple occupancy room? And how do you calculate the number of portable devices needed?
So we work on different simulations with multiple people, in different rooms, especially for classrooms. And basically, we are always saying the same situation, meaning that the amount of air blown by this treatment unit can increase a lot the dispersion of the particles. So as we saw in the previous presentation, it's key to know where to put this device, and it's highly related to how this device is working. Is it the air, is it blown from the top face? Does it have an angle or not? It's a very complex problem to handle, and that's why with the simulation it's quite easy to see the things, but if you don't have that, it's quite hard to guess how to optimize that. And it's the same for the number of device that you can put in a room. If you consider the room as a wall, then it will be quite easy to assess that the more device you put, the quicker will be the extraction of the particles. But on top of that, if you think about quite local issues, the more device you put, the more air you are blowing inside the room and the more dispersion you have. So it's a balance, again, between location and optimization of the airflow.
Of course. And would multiple small devices be better than one large device?
I would love to answer to this question, with a general statement, but again, it's highly dependent, of what kind of device you are considering. I don't have the general statement. But
that's a good answer. Thank you. I will read a comment from Professor Pittet. So in our institution, we work with 99.9% efficiency HEPA filters, and the pre-filters are extremely important in the survival of the filters. The better the pre-filtration, the longer the use of the HEPA filters, for example, in operating theaters. So where we could keep HEPA filters without changing them for years, up to 4 to 5 years, with no change in their capacity to work based on particular air sampling testing. Does any of you want to comment about that?
I want to second that. Absolutely, 100%. One thing, well, again, codes like, well, I hate to say it, but the code that I'm familiar with is the ASHRAE code, like the American, the American code. They actually recommend that. They recommend 2 banks of filter, a pre-filter. That's key. And it actually helps with the longevity of the HEPA filter for sure. It actually cleans. It actually helps protect the air handling unit as well. So even from the mechanical engineering perspective, that's a great idea.
Thank you. Another question from the chat. So does adding ionization to HEPA improve things or make them worse? Some design for consumerism have both. So what about ionization?
I was asked by a company or a manufacturing company around me to study that. But chain of events, they ended up not wanting to adopt the ionization system. I don't know why. they kind of just ended up not doing that. On paper, it seems it would be a prudent thing to do. I yet have to see a study related to the practical implications of it. And I don't know great many hospital systems that consider using the ionization system. Again, in the United States, those that I'm familiar with, they're mostly looking at air purifiers and HEPA filters and kind of more traditional approaches as opposed to ionization system. Again, well, topic to study. I don't have, yeah.
Thank you. Another question. So could computational fluid dynamic simulation be used to better localize patients in a healthcare facility as part of infection control risk assessment? And for instance, to better localize non-COVID patients in area where ventilation is at its best to reduce nosocomial transmission and protect patients with it's currently a major challenge. Since in COVID units, we have adequate hand hygiene and PPE to contribute to healthcare worker prevention protection, sorry.
Yes, definitely yes. We have worked on different, let's say, situations with mainly French hospitals so far. As I mentioned a bit earlier with La Pitié-Salpêtrière, we work on this post-surgery room where, it was just before the second wave. They were anticipating, the fact that they will have to welcome both COVID and non-COVID patients in the same common space. And they had in mind different locations for the COVID patients. And we can quickly test, virtually which location can be the best to limit, let's say, the transmission between the patient COVID and non-COVID. And in this particular studies, since it was quite difficult, to limit the risk because the Ajax system was propagating all over the room, we virtually also assess what could be the best, let's say, internal wall to set and to put, to try to control and create room inside the room. And if it was a benefit or not to add individual extraction, on top of the patients. And does it make sense or not? What could be the location? So I will say that it's a very convenient tool, to quickly test different ideas and probably find the best combination of mitigation measures that can try to limit the risk.
Thank you. So, and do you think we should perform more CFD simulation before building or renovating healthcare facilities?
Yeah,
so,
that's the big deal. On my point of view, that's the best way to use it. And it's the same usage that you can find in automotive industries or aerospace industries. So the earlier you begin to use CFD simulation, let's say the more weight you have to change your design, because as soon as it is built, it's very hard, to change a location of Ajax system or not. Sometimes you can do that, if you are planning, to change the whole floor or the whole department. But we saw during the COVID crisis that the mitigation measures we can put in place are very limited. But sometimes, as soon as you understand pretty well the airflow, you can always find solutions. It's probably not the best one, but it's improving the situation. But definitely, yes, as a design phase, it's more powerful for sure.
Thank you. And finally, we have a time for a last question from the chat. So why not disinfecting the air directly with, an example, hypochlorous acid, which is supposed to be safe to inhale at low concentrations?
Sure. Yeah, why not? Yeah, I'm with you. Why not? But again, that is a definitely an excellent suggestion, but I don't think, in my opinion, I don't think it will replace the types of conversations that we have, both Emmanuel and I had throughout this presentation. I think it's to a sense, it's an addition to what we're trying to achieve here. Because a lot of times, especially for COVID-19, we were in a dire need of PPEs, let alone, the clean. Well, it's not always going to be. I mean, I think still looking at the system, the building, as a living entity and then try to optimize its performance using CFD, using experiments, using techniques and approaches. I think that's still needed. And then additional solutions and approaches are always, in my opinion, welcome, like most welcome.
Great. So thank you both for the excellent presentation. This was very nice, and thank you for the discussion. Thank you for all the questions from the chat. Now I welcome you for the next session with the sponsored symposium about hospital hygiene to keep people safe. Thank you.
It's a pleasure. Thank you.
Thank you.